So let me just read your problem. This is later on in the lesson, but this is the direction we're heading. Air is being pumped into a spherical balloon. At a spherical balloon.
I finally see why people say, oh,
Okay. Air is being pumped. Are you following me so far?
yes.
Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay? You guys need to listen to this so I can set up the rest of the lesson. Find the rate of change of the radius when the radius is 2 feet. So, what's the title of the lesson? Related rates. Listen carefully to the problem again. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. What two rates are in this problem? The rate of the change of the volume of the balloon and the rate of change of the radius. You guys following? If the volume of the spherical balloon is expanding, what also is changing? The radius and the volume. Do you understand why these are called related rates? If the volume changes, the radius changes. They're dependent on each other. Okay? Now, what does this have to do with calculus? A rate of change is a slope. How do we find slopes? Derivatives. Okay? Does anybody happen to know the volume formula of a sphere? I don't expect you to remember this. It's 4/3 pi r cubed. Okay, listen. Hey. But what's the rate of change of the volume? If the volume is 4/3 pi r cubed, what's the rate of change? We have to take the derivative, right? So this lesson is going to involve derivatives, but listen carefully to this next question, because this can help you make better sense of all of these problems. You guys ready?
Yeah.
If you take a derivative, you have to take it with respect to something. Right?
Yeah.
Listen again to this problem. The rate of change is 4.5 cubic feet per minute. The rate of change of the radius, we're going to have to find that in terms of feet per minute. So the rate is changing with respect to what variable? It's feet per minute, so we take the derivative with respect to time. Because what determines the amount of change? It's how much time transpires. Do you guys understand what I'm talking about?
Yeah.
So if we're taking the derivative with respect to time, that means t is not a variable in our... in that formula, volume equals 4/3 pi r cubed. Is t even a variable in there?
No.
So this is implicit differentiation. You guys following? If we're taking the derivative with respect to a variable that's not in the equation, that's implicit differentiation, isn't it? Like, what's the derivative of y with respect to x? It's dy dx. It's implicit. It's dy dx. So we're taking the derivative of all these values with respect to time. So that means this is all implicit differentiation, and there's always going to be two rates, and we have to figure out what relates the two rates. If the volume expands, the radius changes. Okay? You understand what I'm talking about? Or this problem here. When water is drained out of a conical tank, the volume, the radius, and the height are all functions of time. So if water is being drained out of a conical tank, isn't the amount of the water changing? But isn't the height of the water in the tank also changing?
Yes.
And if it's, you guys want to know what a conical tank is? It's a tank in the form of a cone. So then wouldn't the top of the surface water be a circle? So as the volume of the water decreases, doesn't the circle shrink? So then the radius changes? Those are all related rates, the volume of the water, the height of the water, and then the radius of that top circle of the water. Those are all related rates, right? These are all problems we're going to have to talk about. Okay? And they really aren't as bad as they seem. Okay? So, Let's first just talk about related rates in the context of an algebra problem. No words yet. Here's example 1. We have this equation or this situation. Suppose x and y are differentiable functions of t. So x and y don't represent unknown values. X and y represent unknown functions of t. And x and y are related by this function, y equals x squared plus 3. Find dy dt. Now, if this were a contextual or an application problem, they would say find the rate of change of y. Do you understand what I'm saying here? Dy dt means find the rate of change. That's because that's what a derivative is a rate of change. But it says find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Oh, I said dx dt, didn't I? Yep, but I didn't write it. It's dx dt. All right. So we're taking the derivative with respect to what? With respect to t. Because x and y represent functions of t. So when we differentiate, it's with respect to t, which usually stands for time if this were some application problem. So this equation, y equals x squared plus 3, we need to take the derivative with respect to t. That now means that both of these are implicit differentiation. This side here and x now has to be differentiated using implicit, because we're not taking the derivative with respect to x, it's with respect to t. So what's the derivative of y with respect to t? dy dt. Try to listen very carefully. What's the derivative of x squared but with respect to t?
2x dx dt.
Exactly. It's 2x dx dt.
Now we can't factor it out now.
Exactly. Yep.
Now, these are all great questions, you guys. I got one. Do you understand now why these are called, or we're not actually?
Do you understand why these are called related rates? Don't we have two rates now? dy dt and dx dt. The problem is we can't solve for one rate if we haven't been given the value of another rate. Does that make sense? That's why they gave us this. And that will always happen in these application problems. If they want us to solve for one rate, they'll give us the other rate. Okay? Because you notice in that problem I read to you at the beginning, let me read it again. Air is being pumped into a balloon at a rate of 4.5 cubic feet per minute. There's the rate that's given. That's dV dt, or the rate of change of the volume. Okay? Anyway.
So then we
What happened to the 3?
it's 0.
It's just 0.
It lasts.
Okay? So what is dy dt? That's what they're asking for.
Now it's 4.
2x times 4.
4.
You have to plug in your known values. So it's 2 times 1 times 2, because dx dt is equal to 2. So dy dt is equal to 4. That's all related rates are. That's all you do.
Okay. The problem lies now in you're going to have to come up with your own equation. Okay? But a lot of times it's as simple as remembering a formula. Like if we're talking about the rate of expansion of a circle, the area of a circle, then what's the formula that relates the radius to the area? Pi r squared. A equals pi r squared. There's your equation. Okay, so a lot of times, especially if it's a geometric problem, it's just as simple as remembering a geometric formula. Okay? So let's do this first problem here. Example 2. This is an actual,
We're doing this for real, guys.
for real.
Strap it up.
A pebble is dropped into a lake I'm going to use the words from the book. It's dropped into a calm pond.
So what is our factor?
Is it a completely circle pond?
Causing,
Good question.
well, if you drop a small pebble into a surface of water that's not rippling, what happens when you drop the pebble into the water?
The ripple.
But how does it just go in one direction? What happens?
In all directions.
It expands in concentric circles, right? So don't the circles continue to get bigger and bigger?
Forever.
Until they disappear.
Okay? But if the area inside of the outer circle is expanding, that means the radius is also expanding of that outer circle.
Right.
So anyway, causing ripples in the form of circles. The radius of the outer circle is increasing at a rate. Now this is the word you need to pay attention to. They've given us now one of the rates. At a rate, constant rate, of 1 foot per second. When the radius is 4 feet, at what rate is the area and they call this the disturbed water. That makes it sound freaky. The disturbed water is the water that has the ripples that are expanding. I think they're blowing out the sprinklers out there. Winterizing. So you guys, they're asking us to find a rate. But what is the rate of the area expanding connected to? The rate at which the radius is changing. If the radius grows, the area gets bigger. So those are the two related rates. The rate of change of the radius and the rate of change of the area. So what we have to come up with is one formula that connects the area to the radius of a circle. And we know it. A equals pi r squared. That's a formula that connects the radius to the area. These are called related rates, so we have to have a formula that relates the two variables, the area and the radius. Now, let's make a list of what we know. What do we know? What is this right here? That's the rate. So we're not going to say r equals 1 feet per second. That's this right here. That's dr dt. dr dt equals 1. The rate of change of the radius is 1 feet per second. So that's dr dt. Okay.
What else do we know? We need to find, what do we need to find?
The equation.
We need to find, when the radius is 4 feet, at what rate is the area changing? So is that A?
What is A?
Are we trying to find A or dA dt? They want the rate of the area change. We need to find dA dt when the radius equals 4. You guys need to understand something important here. The radius is changing at a constant rate, but the area is not changing at a constant rate. So that's why they say find the rate of change of the area when r equals 4. When r equals 4, it's changing at a certain rate, but as the rate of radius continues to increase, it might increase at a faster rate. Yeah.
So if that's only one point of time, then what is that doing you any good?
Right now, it's kind of hard to answer that before knowing a little more about derivatives. It's called an instantaneous rate
Okay.
of change. We do some more application problems later on that might make it more clear,
Okay.
but it's kind of hard to answer that right now.
Okay.
But you are right. It's the rate of change at one instantaneous moment of time. And in a lot of application problems, that's important, especially the business and economics world. But we'll have to wait a little bit before we can get into that. So how do we find dA dt now? Because dA dt is not part of our formula here. But we don't have dr dt either. We have to take the derivative of this, you guys,
With respect to dA.
with respect to time. So,
With respect to d over dt.
yeah, it's going to be d over dt. Yeah, so
So,
what's the derivative of a with respect to time?
d over dt.
It's dA dt.
Then you got pi.
Now, a lot of students make a pretty critical mistake here. Is this going to be a product rule? What do you think? Pi is not a variable, you guys. Pi is a number. Okay? I know it looks like pi times r squared, and it is pi times r squared, but you only use the product rule if you're multiplying two unknowns. Okay? We already know pi is 3.14, so this is not a product rule. This is just the power rule. Okay? Well, let me show you a different problem.
Oh no, because that's like 2x.
What if it were 3r squared? How would you find the derivative of that?
Drop it down.
You drop down the 2, but then it multiplies 3, so it's just 6r, right?
So it's going to be 2 pi r.
So what if it was pi r squared? It's just 2 pi r.
With
With
dr
dr
over dt.
dt, because it's implicit differentiation. Okay? So back over here we have 2 pi r dr dt.
And we already have one of those equations.
Now what do we have?
dr dt equals 1.
We have dr dt, and what else do we have? And we want to find dA dt when r equals 4.
So we got 8 pi.
So dA dt, all we got to do is plug in values. 2 pi times
4.
4 times
1.
1.
8 pi!
So the rate of change, when r equals 4, the rate of change is 8 pi.
That's so sweet.
Let's talk about that balloon problem now.
Can't get on the court.
Example 3. Air. Well, let me go back. We do need to be a little more exact. 8 pi what? Sorry, I forgot to do this. Feet per second. There we go. Well, actually, we need to be even more exact than that. No, we don't need to multiply it out, but the area of a circle is not feet per second. It's feet squared per second. There we go. Air is being
There is a b.
pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Air is being pumped into a spherical balloon. So we kind of already talked about this. If you pump air into a balloon, the balloon expands, right? Now, a lot of things are changing. The surface area, the size, the height, a lot of things are changing. But which two particular rates are they interested in here? The radius, the rate of change of the radius, and the volume. What's that?
So it says where you just find any rate of change related to another rate of change on that balloon, whether it be surface area or anything like that.
You'd have to have the appropriate values, but yeah. So this right here, you guys, is a change of volume. So that would be dV dt. And if we've been given dV dt, and we're supposed to find dr dt, our first task then is to find an equation that relates v to the radius, the volume of the sphere. Okay? And if this were a test question, I would give you the formula. I don't expect you to remember the volumes of a sphere formula off the top of your head, but volume is 4/3 pi r cubed. Now, probably not. So we're gonna use these often enough, at least the important geometric formulas. But you guys, the other thing that's important is you choose a formula that only has the values you want. What if we had other unknowns in there, like h or other things, and we don't have any of those values in the problem? You see how that could be an issue?
Yeah.
So you've got to make sure that the formula you choose to use only has the quantities that you've been given. So what do we know? We know dV dt is equal to 4.5. We need to find dr dt when r equals 2.
So then we gotta find all these to respect to d.
So now we got to take the derivative
So we got
d dt. We need to take the whole derivative of that thing with respect to time. So it's going to be dV dt remember, pi is not a variable, it's just a number. So the 3 would drop down, and then it would change to a 2 here. But then the 3's cancel, so it's 4 pi r squared. Keep going. Good, dr dt, because remember, this is implicit differentiation. So now plug it in. We knew dV dt was 4.5, and we know the radius is 2, and we're supposed to find dr dt. So it's just simple algebra now. How do we get dr dt by itself? Divide by 16 pi. So dr dt is equal to 4.5 over 16 pi. We have to label this according to the correct units.
cubic feet.
Well, cubic feet was the volume. It had to be cubic feet because you measure volume in terms of
Cubics.
cubic. Yeah, I guess cubics. Feet cubed. But a radius, how would you measure a radius? Is it feet, feet squared, feet cubed? A radius is a radius is a linear measurement that has no dimension other than one straight line. So it has one dimension. It's linear. So it's just feet per second. The radius is changing according to that rate. Oh, per minute. You're right. Sorry.
We would have docked you, but that's okay.
You would have docked me.
Just a point.
But again, you guys, is the radius always changing according to that rate?
No, it's just at that instant.
Only that instantaneous moment. A derivative is an instantaneous rate of change. It's not an average rate of change. Okay. Now, you guys, if this were multiple choice, listen, you guys, if this were multiple choice, and this does not appear as one of your answer choices, what does that mean they probably did? Simplified. If this were free response, I'd be okay if you left it like that. Okay? So just keep that in mind. Let's keep going. These are so much fun.
Yeah, Mr. Huff. Ooh, can we do like a really exciting story problem?
Yeah.
Yeah, like
Like a
what
car
if
chase.
somebody
Do a
shot?
car chase. Car chase. Car chase.
Example 4.
You like trying to see how to get back before it's like kill him or something. He's out. I don't know how to do that.
A television. We all like television, right?
Yes, sir, Mr.
A
Huff.
television camera at ground level is filming the liftoff of the space shuttle.
Oh my goodness. This is rocket science.
It's rocket science.
We are doing this. Yes.
That is rising vertically according to the position. Now we're getting some physics here. The position equation. S equals 50 t squared where S is feet and T is seconds. The camera is 2,000 feet from launch pad. Wow, this is an involved problem. Here's the actual task. Find the rate of change in the angle of elevation of the camera. It's going to involve trig at 10 seconds after liftoff and 3 seagulls. I made that up. Just 10 seconds after liftoff.
Wouldn't even be surprised.
If a seagull passes by and creates a shadow,
Use that shadow.
As the sun is rising at a
Use
constant
that
rate.
shadow to solve it.
wait, we don't know what time zone they're in. They're in the Pacific time zone. All right, let's draw a picture. Oh crap! I gotta draw a space shuttle.
It's got a perfect. It looks like a fish.
There's a space shuttle.
I've never seen a shuttle that's looking good.
That's a space shuttle, you guys. There's a little astronaut looking out, saying, "Hey, bye, mom."
If these
And
things out,
then
he's gonna pull out.
there's a camera guy here saying, "Hey, that's cool." He's got his little camera there in his,
This is on the ground.
and he's on ground level,
How are they supposed to film it if the camera's on the ground?
and he's 2,000 feet away.
Angle the camera.
And then we have this angle of elevation theta. So let's let theta be the angle of elevation. Okay. Holy moly. All right, well,
I'm going to talk a little bit while you guys are still writing. The angle of elevation is changing, obviously, right? Because the rocket continues to go up. But the rate at which the angle changes depends on what other rate. How fast the rocket is moving, right? The speed of the rocket. If the rocket increases its speed, doesn't the angle of elevation change faster? Did they give us the speed of the rocket? They gave us a position function. Now think back to some of your physics classes. If we have, or I think we actually talked about this in here. If you have a position function,
The position function is the velocity.
the velocity is the derivative of the
position function, exactly.
Everyone who's
So, S equals
Oh, I'm
50
excited. I don't care.
t squared, so ds dt is 100t, right?
Yes.
That's the velocity.
Oh, yeah.
Okay.
Dude, I'm gonna go tell Mr. Starling he's gonna get extra credit for doing the problem.
Now, what are they asking us to find?
Angle of
Rate
elevation.
of change is the angle of elevation.
Oh, do they want the angle of elevation? They want the rate of change, so that's d theta
Oh, jeez.
over dt. When t is equal to 10 seconds. Now,
How do you relate angles to velocity?
think trigonometry, you guys, and think right triangle trigonometry.
We gotta find the tangent.
Tangent. Okay, exactly. Why tangent?
Because you're not caring about the hypotenuse. You're caring
We don't
about the height.
care about this distance. We care about the height here, and we already know how far away he is here. Isn't tangent opposite over adjacent?
Yes.
But the one thing we don't know is how high the rocket is at 10 seconds.
Plug it in.
But we have the position function, not the. Well, I guess we could use the velocity, but we have the position function, don't we? So use
10.
S equals 50 t squared when t equals 10 to find the position of the rocket after 10 seconds. So 10 squared is 100. 100 times 50 means that the position is 50 large.
So we can write that on here, right?
Actually, no, wait, that's one too many zeros. Dang it. 50,000 would be like halfway to the moon.
100.
5,000. Hey, what's that? When t equals 10. Yeah.
That would be before launch, isn't it? T was
Yeah, t equals 0 be at launch. Okay. So you guys. Oh. So, some of you had the great idea to use tangent of theta. I don't remember who it was. But the definition of tangent's opposite over adjacent. Now, the adjacent length is set. He's 2,000 feet away from the base of the rocket launch. Okay? This distance here changes, right? Depending on the height of the rocket. So, what variable do we want to call this?
Well, are we finding it when T is 10?
H for the height.
We could call it h for height. Now,
at 10 seconds we know the height, but in general,
Okay.
we really don't know. So the tangent of theta is equal to h over 2,000. Okay? That'll allow us to find the angle of elevation at any height, at any given time of t. So the question, you guys remember what the question is. We can't get lost with with everything they're doing that we forget the question. Find the rate of change in the angle of elevation. We're not supposed to find the rate of change of the height of the rocket. We're supposed to find the rate of change, so it's d theta dt. Okay? Here's the equation, though, that relates the height of the rocket to the angle of elevation. So this is what we need to take the derivative of with respect to time. Because as time passes, the height changes and the elevation of the angle of elevation changes, right?
Yeah.
So we're taking the derivative with respect to time. D dt, and over here the derivative with respect to time. So, what's the derivative of the tangent? Oh man, secant squared. So it's the secant squared of theta. But remember, this is implicit differentiation. This is a chain rule. We took the derivative of the outer function, which is tangent, but now we have to take the derivative of the inner function, which is theta. We're not taking the derivative of theta with respect to theta.
It's d over dt.
It's d theta
Over dt.
dt. We're taking the derivative with respect to time. And so theta represents a function of time, so the derivative is d theta dt. Alright? We're going to do a few more of these problems. This is not the last one. I think this is going to take a little bit of time to wrap some heads around. What's the derivative of this? H over 2,000.
It's closer to null.
Let me write this a little bit differently. Let me move this over here. Do you guys agree with this?
Yes.
Yeah.
So then what's the derivative of that? Okay, let me show you something easier. What about this? What's the derivative of that?
2.
Just 2, right? So then over here, what's the derivative of this? 1 over 2,000. But remember, we're taking the derivative with respect to time. So it's 1 over 2,000 times dh dt. We good now? Well, actually, you know what? We're using the wrong variable here. And now that I go back and look, didn't we already define the variable for the height?
Yeah.
Look at what we defined it as. We defined it as its position, s, right? So we should actually change that to s. I forgot about that last time. We're making up all these new variables. So it's s over 2,000. So the derivative is 1 over 2,000 times ds dt.
You gotta get all the dt's so those are different.
So we can't lose sight of what we're trying to solve for. Are we trying to solve for theta, or are we trying to solve for d theta dt, or are we trying to solve for ds dt? D theta dt, right? So if we're trying to solve for d theta dt, that means we have to know ds dt, and we have to know theta.
And we do know it
Yes,
ds dt is right here. It's 100t, and we also know t. T is 10, so we'll plug that 10 in there. But are we missing something here? What is it? We don't know theta.
And if we don't know theta, we can't find d theta dt because we'd have too many unknowns. We can only have one unknown in this problem.
Well, theta's going to be changing.
It's going to be changing, but they want the value of theta at time equals 10 seconds.
Well, then you can find the position, and then you can use the inverse tangent to find theta.
Do you guys hear that? We don't have to know all the tangent or all the theta values. We just want to know the theta value at 10 seconds. So what was your idea, Alex?
You figure out the position with the information we're giving at time 10, which is 1,000, so you know.
Well, that's the velocity. The position at time 10 was 5,000. So we have theta here.
I forgot that was the derivative form.
Yeah.
My bad.
He's 2,000 feet away. I didn't draw this according to scale, obviously, but at time equals 10 seconds, he's 5,000 feet up.
So why didn't we just do that originally? Why did we go through everything else?
To show us.
Well, this function we had to set up as theta in general, not a specific time value. But now that we have a specific time value for the derivative, we're going to use time equals 10.
Oh, because we're just going to find. Oh, because we have to find. We're not looking for theta, we're looking for
d theta, d theta. Yeah. So, you guys have calculators, get them out. Let's do the inverse tangent. Theta is the inverse tangent of opposite over adjacent.
Alright, so we got to do the inverse tangent, second tangent, apply. Yeah. 68.198590.
Okay, guys, we're losing a little bit of focus here. Your calculator has two modes, right? Radians and degrees. We ought to be in radians. We ought to be in radians for this problem, yeah. So change your calculator to radian mode. Yeah. What's that? Radian represents more of an... That's actually really hard to explain. Let's finish this problem, then I'll explain why. It has to do with the unit circle and using radians with the unit circle. But
What's radians giving you? Sort of,
the measure of the angle in radians.
yeah.
Because we have to know the measure of the angle to plug that into right here.
What would you do? Sorry, I'm trying to figure it out with does it just mess with the problem itself?
Radian is more of an actual measurement using like feet and miles and things like that. Because a radian is an actual measurement around a circle, physically around a circle, which we can measure in actual units. Does that make sense? Degree is just an angle measure. Does that make sense? A radian measure is an actual arc length around a circle, which we can measure in feet. And that's what we're in here. Is it feet or miles? What are we in here? Is it feet? So the reason we have to use radians is because we're actually using measurements in feet, and radian is a foot measurement.
So you use that next time you're trying to measure something involving height or distance or anything that involves
Yeah.
means grams.
Yeah. Because radians can be measured using feet, and degrees can't. Okay.
That makes sense. That was one part.
I don't even know where we are now.
I changed it to radians.
Where are we?
We're plugging in data for because we found out that there's tension.
So it's going to be so this is going to be an approximation, I'm sure. It's not an exact answer.
1.2.
Let's do 3 decimals. 1.190.
190. So 2 decimals is 1.190.
All right, we'll just do 1.19. Okay then. What else are we missing? We know theta now. Did we ever have dsdt?
Yeah.
Yeah, the parentheses.
dsdt is 100t, but t is equal to 10. So 100t is 100 times 10,
1,000.
which is, so we know dsdt. We know theta. And we're trying to find d theta dt. So how do we isolate this?
Isolate.
We got divided by secant squared of theta.
We can divide by
Secant squared. So 1.1.
okay. Okay, I see. We could do that. But then, all right, watch this pretty closely, guys. You guys see what I did there? If you're dividing by secant squared, isn't that 1 over secant squared?
Yeah.
And what's 1 over secant squared?
Cosine.
It's just cosine squared. You follow what I did there?
Yeah.
That's the reciprocal.
You just have to remember that. Basically.
Well, 1 over secant is cosine.
And it'd be the same with secant squared.
And 1 over secant squared is cosine squared. Yeah.
You're using trig.
It's trigonometry. And do we know theta?
No.
We do.
We did it. So 1.9.
It was 1 point something. Approximately 1.19. So now we have cosine squared of 1.19 times 1/2000 times 1,000.
Then we just do that. So that's going to be 1/2.
And that's d theta dt. That's equal to d theta dt.
Oh my gosh.
How do you do cosine squared in calculator?
Just do cosine times cosine. Cosine of 1.19 times cosine of
There's no
1.19.
variable.
That's right, there can't be any variable because we're solving for d theta dt. So that
Wait a
means
second. Okay.
we don't want there to be any variables, otherwise we couldn't solve for d theta dt.
Okay, so like.
So as long as you can
what's that
simplify
saying?
this in a calculator,
What's that equation saying? Like.
this is the rate of change of the angle of elevation. It's d theta
Oh, okay. So
with respect to time. So as the rocket's going up, the angle,
changing that.
the rate of the angle of elevation is changing.
Okay.
So wouldn't it just be cosine squared of 1.19 times 1/2? Because it's.
Yeah, 1,000 divided by 2,000. Yeah, so we could do cosine squared of 1
If that's a rate,
.19.
shouldn't there be a, oh. Oh, there's a measurement. So that's.
It's going to be in terms of
Or
radian.
radians per second.
Radians per second.
Okay, now that makes sense.
And I got
It's cosine times cosine.
I got 0.07.
What's that?
Would you put just cosine, cosine to get a number?
No, cosine of 1.19 times another cosine of 1.19 times 1/2. We got anything yet? You got 0.07? You got 0.07? Anybody else over here?
I got 0.07.
0.07.
So it's 0.07
No.
radians per second. So the rate of change of the angle of elevation is about 0.07 radians per second. Let's do another one.
Okay, to find out, say you want to find out the percent, you just have to find out the
Yeah. Focus, 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 you guys. These are not the easiest of problems. And if they sure seem easier when somebody else is doing them here for you, but when you have to do this on your own, they aren't easy. So focus.
Now you understand why the error scares me.
It's ds dt. It's 100t, and then time is 10 seconds. All right, here we go. Matter of fact, let's do one of your homework problems here. This is number 33 off your homework from 2.6. So, a person 6 feet tall walks at a rate of 5 feet per second. Whoa.
That's not walking.
That's pretty fast.
You've got a really small torso.
Wow. 5 feet per second. Anyway, I would say he's jogging at a rate of 5 feet per second. But anyway, from a light, or away from a light that is 15 feet, so like a lamppost, I guess, above the ground. When the person is 10 feet from the base of the light, how fast is the tip of his shadow moving? You better draw this out.
Yeah, we're just shadow we wouldn't say for you.
That's what I was thinking.
Because as he walks further away from the light, doesn't his shadow get longer?
I don't know.
Oh, is it dark outside?
It must be because there's a shadow.
Well, it could be light, and it could be just light from the sun. The light could be turned off.
We're assuming it's from the light.
That'd be dark.
Only 13 feet above the ground, kid.
I know, but you still have shadow.
You know what?
No, but in the front, you have the light 15 feet above the ground.
So we got this light source here.
We're on the same page.
Okay. We got this person. So the guy or whoever this is 6 feet tall. And then the light is 15 feet tall. That's pretty much all we have to go on.
So we know how fast he's walking.
Yeah.
Oh, okay, we know how fast he's walking. He's walking 5 feet per second.
So when he's 10 feet away, he's only gonna walk 2 seconds.
Walk.
Walk for 2 seconds.
He's walked for 2 seconds, yep.
Oh, I didn't know.
Well, when the person's 10 feet from the base of the light, how fast is the tip of the shadow moving? So, here's what I want you guys to do for about, I'm going to give you guys 12 minutes. I wish I could give you a little more. I'm going to give you guys 12 minutes. I want you to get into a group. Okay? easiest way to get better at these problems is just to try to figure them out without having somebody say, here's what you do next, here's what you do next, because not every problem is exactly the same. I can't show you a list of steps and say do this, and then do that, and then because every problem is different on these related rates problems. You've got to be able to be creative, formulate some kind of way that you're going to solve it, keep track of what you know, what you're searching for. Okay? It takes also a level of comfort being uncertain at times, because that's okay to not know. All right. So get in a group. We'll see how far you can get. We'll give you about 10 minutes, 12 minutes tops.
So where's your proportion? Okay, well let me help you. So you got 15 and 6, right? 15 will equal your total distance, S, divided by S minus X, because you're looking for the length of the shadow. The total distance, X is just the length of the shadow. Well, X is this one. Okay? The total distance is X. So the length of the shadow is going to be S, the total distance minus the X, which is just 0. Correct?
The total distance minus what that is.
Total distance minus that gives you that.
Yeah, S minus 10.
S minus X.
All right, you guys, check this out.
Then you cross multiply by. So cross multiply by, and tell me what you get. Leave it as an X, don't put it as a 10.
So they have given us, I know they have given us particular values like X is 10, but in general,
It does give you S equals 5/3 X.
in general, couldn't we say that X is to 15? Well, actually, we could say X plus Y is to 15 as Y is to 6. Do you guys, do you remember this from geometry? This would be like 4 years ago from you guys. Similar triangles.
And similar triangles, you can set up a proportion. So this length here is X plus Y, right? So X plus Y is to 15 as Y is to 6. Do you understand what I've done here?
Yeah.
Okay. Now, the one piece of information that they gave us, other than he's 10 feet away, is how fast he's walking away from the light source, right? So if he's walking away from the light source, is that dx dt or is that dy dt? He's here and he's walking that way, right? So x is changing. So the rate at which he is walking is dx dt. That equals 5.
You got that part, yeah. Challenges. Except not part of X.
Now, what do you think back a long time ago in a galaxy far, far away? Do you remember how to solve these proportions?
I didn't want it, I just was wondering.
You cross multiply these, don't you?
Yeah.
I don't know. That was awful.
So X over 15.
Wait a minute, 6x plus 6y equals 15y. But think back to what we've done now at this point with all the other related rates problems.
Oh my.
We took a derivative with respect to time. We've taken a derivative with respect to time. Okay? So if we took a derivative with respect to time, and then here we took a derivative, oh that's so good, with respect to time,
dx dt
Plus 6y
plus 6
dy
dy dt
equals 15 dy dt.
Sorry, I'm in your way. Let me move. I was reading here.
Let's get my way.
I'll move over here. Oh my word. Oh, cute.
Why aren't you trick-or-treating class?
I didn't bring any candy today.
I don't want to
Alright.
you.
Now what?
Now you simplify it.
Do we know one of these unknowns?
dx dt.
We know
It's the Halloween.
we know dx dt is equal to 5, so that changes it to
How do we know it's equal to 5?
because he's walking at a rate
Oh, 5.
of 5 feet per second. So that equals 30 plus 6 dy dt equals 15 dy. We've got to manipulate this a little bit here. Yeah, we've got to move some things around.
How'd you get 30?
Minus the 6, I want to keep it positive.
Minus the 6, so we have 30 equals 15 minus 6, and then I'm going to factor out the dy dt. So that equals 9 dy dt, and that equals 30. Divide by 9, and then, oh crap, 30 over 9,
Just divide both by 3, that gives you 10/3. That was right.
10/3. Now hold on. What is d? I know dy dt is 10/3. That's not what I'm asking. What is dy dt?
Shadow.
Thanks.
What's the show?
Basically, the shadow.
It's if this is y right here,
Yeah.
it's the rate that his shadow is lengthening out.
Yeah, but we want to know where
Right.
that shadow.
We want to know how fast the tip of the shadow is moving. So hold on, let me explain that one more time. Okay, the way that I've drawn this, y is equal to the length of his shadow, right? So that means dy dt is the rate at which his shadow is changing. But the question asks how fast is the tip of the shadow moving. So what else is affecting his shadow changing? It's also the effect of him walking forward, right? So it's dx dt plus dy dt. Did you guys hear that?
Yeah.
This right here is the length, or sorry, it's the rate of change of the length of the shadow. But that's not the only thing that's affecting the rate of change of his shadow. It's how fast he's walking as well. He's walking 5 feet per second, and his shadow length is changing at 10/3 feet per second. So if you add 5 plus 10/3,
15/3.
oh man, I was going to go over there and kick your butt. It's not 15/3. It's 15/3 plus 10/3. Is that what you were trying to
That's
say?
what I was about to say.
Which is
I hiccup though.
25/3. What are we in terms of feet? Feet per second. Now the funny thing is, you guys, this was one of your homework questions. The funny thing is, part B was how fast is the length of his shadow changing? That's just 10/3. So we kind of had to answer B before we answered A.
That's weird.
So anyway, yeah.
Moving and the shadows.